Hi, I'm Yue. I'm a senior researcher at Alaya Research. Today, I will present our work on instance-level Trojan attacks on visual question answering using adversarial learning in neural activation space. This is a collaboration with Hideo Chiai and Jun Sakuma. Trojan attacks on multimodal models leverage combinations of Trojans to mount sophisticated attacks. As an example, in the visual question answering VQA task, it aims to predict the answer to a given question based on the presented image contents. We can consider an attack, try to perturb the image, and introduce a specific malicious token, causing the model to produce incorrect predictions. In this given example, the image of this dog is perturbed with some specific perturbations paired with this malicious token frame. Then the output of the visual question answering model will be modified from yes to no. And in this study, we basically focus on the fine-tuning phase of the VQA model. We found that the existing method usually has a reduced efficiency and effectiveness after the model being fine-tuned. A Trojan designed for the pre-trained model may not retain its effectiveness in the fine-tuned model. Attack becomes ineffective after the fine-tuning of the fusion network of the VQA neural network. As a result, the threat model we considered for this Trojan attack research is first, the last few layers of the pre-trained model are replaced with the black box fine-tuning network. The attacker has no idea about the black box fine-tuning networks, but it will have access to the VQA model. Attacker has access to the pre-trained part of it and can add a small amount of data to the fine-tuning dataset. It cannot directly modify the fine-tuning dataset. It can only influence the model training by adding additional samples into the existing fine-tuning dataset of a user. Existing multimodal Trojan attacks usually face the challenges in achieving both the steadiness and the effectiveness, often resulting in either sample inefficiency or easy discoverability by defenses. They have yet to adequately address the three critical factors: the adversary sample efficiency, the visibility, and the variety of Trojans, and their robustness to model fine-tuning. In this study, we propose the adversary learning in neuron activation space. This method compresses two specific neurons in a specific perturbation layer in the pre-trained model to produce overly large neuron activations for each modality. Then through an adversary learning process, a connection is established between these perturbed neurons and a malicious output of the fine-tuned model, so that we can adapt these Trojans, aiming to cause the overactivation of these neurons to the fine-tuned model efficiently. We choose a fusion layer in the visual question answering neural networks as a perturbation layer, since it's usually preserved in fine-tuning to combine different modality representations. The Trojans are generated using multiple iterations of gradient descent. By default, we target the neurons that have the strongest connections to the next layer, as they generally have a larger impact on the model's prediction and behavior. The graphs on the right-hand side illustrate the activations of the perturbation layer before and after the text. The generated Trojans cause the targeted perturbation neurons to produce significantly larger activation values compared to their original states, which are highlighted in white and yellow. The white pixel here is the text perturbation neurons output, and the yellow one is the vision perturbation neurons output. Another example shown here is the optimization trajectory. When we try to find the text perturbation neurons optimized output, we iteratively adjust the output of the text perturbation neurons by modifying the input text representation. And after several iterations, we can select a token, in this case is frame, as the malicious token and replace the last token of the text input. We try to visualize the distribution of such Trojan samples, and we found that this generated Trojan samples does not significantly deviate from that of other benign samples, which renders a more challenging detections by defense methods compared to existing methods. After that, during the fine-tuning, the pre-trained VQA model, the FVQA, it's comprised of three parts: the vision, text, and fusion neural networks. The FVQA is replaced by FVQA fine-tune model. The only difference is the fusion network is replaced by the fine-tuning network. And in our setting, we consider the a fine-tune model is a fully connected network with multiple linear and non-linear activations. The attacker then aims to mount an untargeted attack on the new model FVQA fine-tune by establishing a correlation between the activations of the perturbation neurons and a malicious model output of the fine-tuning model using the Trojans generated from the pre-trained model. During the fine-tuning, the F-tune is updated using the loose L that consists of the classification loose L class and the attack task loose LADV. By optimizing these loose functions, the attacker encourages the model to produce the incorrect answers when the Trojans are presented in the input image and text by building the connection between these overly activated neurons and the malicious output for the fine-tuning model. We evaluate the model performance with different fine-tuning layer deeps. And we found that the proposed Trojan attacks enhance the transferability of the attack to the fine-tuned model greatly, and the adaptation necessitates only a few Trojan samples to compromise the model in the varying fine-tuning layer settings. As a comparison, in the dual key vector, the baseline more than 400 samples are needed to achieve a score of 8.9. In contrast, our approach achieves a score of 0% with just a single shot. Here, the value is the lower the better, and it requires significantly fewer Trojan samples to achieve the better ATA scores here. Moreover, by comparing the mind task accuracy, we can observe that the attack adapts to the fine-tuned model without causing a significant degradation in the mind task performance. Another aspect we investigate is the proposed Trojan attacks the robustness to existing defense methods, including the norm defense clipping and the differential privacy. For the norm defense clipping method, it measures the discrepancy between the norms of the benign and malicious fine-tuning updates. And usually, if the updates has some malicious parameter updates, the norm of such updates will be much larger than the normal ones. But through our method, our result indicates that the proposed multi-Trojan attack can produce the updates with smaller norms, which closely resemble the norms observed in the benign models. which makes the attack more difficult to detect. And this graph here illustrates the performance while incorporating the differential privacy methods. And similarly, the result indicates our methods cannot be eliminated by the differential privacy method. And there is a trade-off between the defense performance and the main task accuracy of the model. A strong application of the differential privacy with a larger standard deviation here can provide some mitigation against our proposed attack, but it may also lead to decreasing the performance of other normal tasks. For example, in this graph, we can see with the increase of standard deviation, the attack task accuracy is also increasing, which indicates a weaker influence of the Trojan samples. But on the other hand, we can also see the main task accuracy is decreasing. So there's the trade-off between the defense effectiveness and the proposed model's main task accuracy. To conclude, in this study, we proposed the instance-level multi-Trojan attack on VQA with enhanced transferability to fine-tune the models. The adaptation necessitates only a few Trojan samples to compromise the model with varying fine-tuning layers. And this study generates Trojan combinations tailored to different input data samples. The distribution of these Trojan samples does not significantly deviate from that of other benign samples, rendering a more challenging detection by defense compared to existing methods. We conducted extensive experiments which demonstrates the efficacy of the attack, revealing that the existing defense methods cannot effectively mitigate the proposed attack. Finally, in the future, we want to investigate the other multimodal learning architectures for VQA, such as the self-supervised learning-based neural networks, and propose effective countermeasures to tackle this attack. Thank you very much. Please feel free to refer to the paper for more details.